Okay, we're going to jump into Bayes' rule, which is kind of like a complicated conditional probability. I'm not going to say too much more about it. Let's go ahead and dive in. So under certain circumstances, it won't be possible to calculate a conditional probability the way we normally do, and instead we have to use Bayes' rule. Now, look at this monstrosity of a formula. I don't like it, and neither should you. In fact, I don't really ever use this formula to do my Bayes' rule problems. I'm going to show you a better way to do Bayes' rule. So let's jump to a problem, and I'll show you how I would do it without even touching this formula. So experts predict that the probability of Texas beating OU is 0.8. Probability of Texas losing to OU is 0.2. Furthermore, you'll get trashed on game day and have hangover with probabilities 0.7 if Texas blows out OU and 0.4 if Texas loses. What's the probability you'll have a hangover? Okay, there's a lot of numbers here, but what clues me into this is a Bayes' rule question is that there's kind of two layers here. The first layer is Texas either wins or loses. And then based on that, you'll have a hangover or not, based on a win or a loss. So there's kind of two layers here, and that's what sets it up for what I like to use for this type of problem, which is a tree diagram. So watch carefully. I'm going to draw a tree where I put win and loss as the first nodes, and then hangover and no hangover as the next nodes. This is the first step for any Bayes' rule problem, is to make the tree labeling your nodes with events. So I'm going to go ahead and say, step 1, label nodes with events. You don't need to label the very top of the tree. We'll leave this as is, but you're going to label your nodes with events. Step 2 is to label edges with probabilities. So let's go revisit the problem statement. It says that the probability Texas beats OU is 0.8. So I'm going to put a 0.8 on this edge here. Naturally, because the probability of Texas winning is 0.8, the probability of Texas losing is 0.2. Now, we are told you will have a hangover on game day if Texas wins, and that probability will be 0.7. So if Texas wins, that is to say, going down this branch, if Texas wins, the probability you'll have a hangover is 0.7, and therefore the probability you won't have a hangover is 0.3. Okay? What if Texas loses? It says that your hangover probability is 0.4. You still maybe drink a little bit even after a loss. So we're going to go down this branch, and it says that we'll have a hangover with probability 0.4 if Texas loses, and therefore 0.6 is the probability you won't have a hangover. Okay, all of our edges are now labeled. At this point, I'm going to proceed with step 3, which is to multiply down the tree. So I'm going to take this 0.8 times this 0.7, and that's going to come out to be 0.56. I'll take this 0.8 times this 0.3, that'll be 0.24. 0.2 times 0.4 here is going to give me 0.08. And 0.2 times 0.6 is going to give me 0.12. At this point, I'm really only going to play with the values in this table. Now that we've done the 3 steps, we can answer just about any question that comes our way. This question says, what's the probability you'll have a hangover? So what is probability of hangover? Well, look at the tree. Of the values that we see on the right, which of them correspond to having a hangover? This 0.56 is just adjacent to the H. This 0.08, that's an 08, believe it or not, is just adjacent to the H as well. So this 0.56 and this 0.08 are going to get added together to get our probability of a hangover. Answer is 0.64. Okay, next question. What's the probability that Texas wins and you have a hangover? Once again, I'm going to look at the right side of the tree, and it says hangover, again, is 0.56. I know my head's in the way, so let's kind of scoot this down. 0.56 is the hangover, but it also comes on the heels of a win. So 0.56 is Texas winning and having a hangover. This is probability of win and hangover. That'd be 0.56. I will not include the 0.08 here because that came on the heels of Texas losing, and I want Texas to win and have a hangover. Okay? And now we have the hard question. This is the question that uses Bayes' rule. This says, given you woke up with a hangover, what's the probability that Texas won? So they want to know probability of Texas won given we woke up with a hangover. Well, I'm going to cite the conditional probability formula like I know and love. So when given hangover is probability of when intersect hangover divided by probability of hangover. Now, when I'm presented with this, I say to myself, what is the probability? I start with my denominator. I just like starting with my denominator. What's the probability of a hangover? Now, the astute among you might realize, well, wait a second, Andy, you already calculated probability of hangover. Well, let's pretend you forgot. Let's just pretend you forgot that I did that. How do I go find probability of hangover from this tree? I go back up to the tree and I ask, which of these four values have me having a hangover? This 0.56 and this 0.08. So those two get added together to make my denominator of 0.64. What about my numerator? Well, again, the astute among you probably realize, hey, wait a second, probability of win and hangover is something we found just a second ago. But in case you need a reminder, the way we get that is by looking at our tree, and I'm looking for the one probability that corresponds to both hangover and win, which is 0.56. So that's going to go in my numerator. 0.56 goes here. That's going to give me a final answer, I believe, of, yeah, I'm pretty sure I know the answer. This is 0.875. And that is your answer to this Bayes rule question. I'm going to do another Bayes rule question on the next page. So we'll reset with a different type of problem. In Austin, 10% of the population suffers from bad driver syndrome. A test can be administered to determine if someone has the disease. When administered to a person who does have the disease, the test returns a positive result 95% of the time. And when administered to a person that does not have the disease, the test returns a negative result 98% of the time. All right, let's talk about a positive and a negative test. Actually, let me go ahead and start drawing my tree before I do anything else. We've got, we'll say I for infected and NI for not infected. So again, is a bad driver and then not a bad driver. Then there's a test. And the test is trying to see whether or not you have bad driver syndrome. And the test can come back either positive or negative. Positive or negative. Positive, just in case we don't know what a positive test or a negative test means. A positive test means that the test says that you have the disease. Now, you might not actually have the disease despite the test saying that you do. This is an important distinction to make here. It's just because the test says positive doesn't necessarily mean you have the disease. We have what are called false positives. The test said you have the disease even though you didn't have it. And then there are also false negatives. The test might say you don't have the disease when in fact you do. So that's what this tree is hoping to kind of resolve. All right, let's go. We've got our nodes are labeled. So remember, step one is label nodes with events, which we've done. I would go ahead and check that off. Step two is to label edges with probabilities. And they told me that the probability of somebody having bad driver syndrome is 10%. So I'll put a 0.1 here and therefore a 0.9 here. If 10% of the population has bad driver syndrome, then 90% does not. Next, the question says a test can be administered to determine if someone has the disease. When administered to a person who does have the disease, so who has the disease, the test returns a positive result 95% of the time. So when we go this way, the test gives us a positive result 95% of the time, and therefore a false negative 5% of the time. On the other hand, when administered to a person who does not have the disease, so now we're going down along this branch, the test returns a negative result 98% of the time. So it correctly identifies a negative for a person who's not infected 98% of the time, but then we'll give a false positive about 2% of the time. Okay, all of our edges are now labeled. So I'm going to put a check next to this. Now step 3 is to multiply down the tree. All right, here I go. 0.1 times 0.95 is going to give me 0.095. 0.1 times 0.05 is going to give me 0.005. 0.9 times 0.02 is 0.018. And 0.9 times 0.98, I need a calculator for this guy. 0.9 times 0.02 is going to be 0.018. 0.9 times 0.98 is 0.882. One thing, by the way, just as a quick sanity check, you should be able to add up all the values in this box, and they should add up to 1. So if they don't add up to 1, you mess something up. In fact, let's just do that. 0.95 plus 0.005 plus 0.018 plus 0.882. I should get 1 and I do. So I know, at least I'm pretty sure, every value on the right is correct. All right, what is the probability that a randomly selected person tests positive? So the question just wants to know, what's the probability of testing positive? Well, let's go look at our table. Off to the right, I see a 0.095 associated with being positive, so I'll pay 0.095. And I also see 0.018. 0.018. And when I add these two together, 0.095 plus 0.018, I get 0.113. Okay. Now, what's the probability that a randomly selected person has bad driver syndrome and tests positive? So, bad driver syndrome and test positive. They want probability of infected and test positive. Well, pretty easy to do. We're just going to go back and look at our table. Which of these probabilities up here has the person both testing positive and being infected? It is simply this value here, just the 0.095. So that's my answer to this question. Okay? And lastly, if a randomly tested person tests positive, what's the probability they have bad driver syndrome? This part is your given. So it's given that they tested positive. But I want to know, what's the probability of bad driver syndrome? So probability infected given they tested positive. We're going to reference that conditional probability formula. Here I go. That would be probability of infected intersect testing positive. And then we divide that result by the probability of testing positive. We could once again cite these values up here, go find what probability is positive, what's the probability of testing positive, but guess what? I already found that guy. That's my denominator, 0.113. So I have 0.113. My numerator is the probability of infected and testing positive, and we found that to be 0.095. So that's going to be my numerator. So now, let's grab a calculator. 0.095 divided by 0.113 gives me 0.841. What's interesting about this is that we know that 10% of the population has the disease. It's in fact, going back to the table or tree, 10% of the population has the disease. And so if I were to pick someone at random, let's go to beautiful face cam. Hi. If I just pick a person at random, there's a 10% chance they have the disease. They have bad driver syndrome. But the moment that I know they test positive, that probability goes up to 84%. It's kind of interesting how testing works. We know that any random person has a 10% chance of having the disease, but the moment they have a positive test result, that probability jumps up to 84%. And we can actually run iterative testing. We could test again. Now the tree would be bigger and therefore way more complicated, but you could test again and rerun the probability and see that the likelihood of them getting a positive result again might indicate, sure enough, they have the disease. These disease questions are fairly common, by the way. Like you will almost always see, someone has a virus or is infected or a disease, and then the second layer is a test that's administered to determine whether or not the person has the disease. So if you ever see a question about probability of somebody having a disease and then administering a test to that person, this is usually a Bayes rule question. Thanks for watching. My name is Andy, and if you found that video useful, we've got plenty more videos just like it. We're giving away a free month of membership, our essential membership to GPA Factory, a free month of it. If you want to get it, just go to this URL and use code YouTube100 to start learning from one of the best to ever teach it. That's me. See you guys soon.